in this class, we've had kind of a sequence of models, and each model is, sometimes they're different, but sometimes there's a situation where each model kind of includes previous models. That's going to continue happening with logistic regression and then with log linear models. So today we're talking about polynomous, which is sort of a terrible word, or multinomial logistic regression. And this, of course, includes logistic regression as a special case. So for binary logistic regression, we were modeling a logit function as a linear function of some parameters and our variables. So for each row, you can think about it as each row of the data set or each row of the table. We have a probability. We have a binomial distribution, and that binomial distribution has linear parameters. And so now what we'd like to do is deal with the case where the response has more than two outcomes. And so, i.e., what we want is a multinomial distribution. So we want y to be multinomial with some parameter vector p of probabilities and some ni. Right, so when I write the ni, again, I'm thinking of like one of these tables where we have, before we had yi and ni, number of successes, total number of trials, and now we'll have successes of type 1, y1i, yi2, and then total. Okay. So the ni's will be these row totals. There'll be big N of them, and there's some grand total. And this is going to be a generalized linear model with a multinomial exponential family with a systematic function that is just a linear function like this. And we're going to have different kinds of generalizations of this logit function that in some sense gives us a logit for each pair here. So if you think about, for example, when we were talking about just models for tables, and we had a table like this, a 2 by 3 table, and we wanted to adapt odds ratios, or this is sort of fundamentally about odds ratios. We wanted to adapt odds ratios models to this. We had sort of 3 choices, at least 3 choices. One of them was partitioning. Another was baseline. And another was, I don't know if we even had a name for it, but this kind of model. Okay? Changing baseline. What do I mean by that? Well, say we have 3 by 2. There are 3 odds ratios that we could consider. I consider this odds ratio, and this odds ratio, but there are only 2 independent odds ratios. Right? So we have a choice as to how to model them. If I pick this one and that one, then I'm comparing this column and this column to the baseline. If I can do this, then I'm comparing this one to the baseline, I'm comparing this one to that. So it's how much does something increase as I go to the next level. Okay. That covers sort of the baseline one, which is compare everything to the first one. This sort of changing baseline guy. So this one has the advantage that it doesn't, as long as I think of something as baseline, like I'm thinking about colors, this is black, red, green, and blue. It doesn't really assume any ordinal relationship among these variables. This one doesn't make much sense if these are really nominal variables. So this one is kind of implicitly ordinal, whereas this one is perfectly fine for non-ordinal ones. And then there's this partitioning idea. So the partitioning idea, right, I do something like I collapse two of the columns, and I look at these two versus this one, like in the tonsils example, and then I look at inside of this column, the thing that I collapsed. Right? So each of these ideas will lead to different strategies for multinomial logistic regression. And there'll be some additional strategies that are even sort of beyond this. But that's the kind of idea I want you to have in mind while we do this. Okay.
Yeah, excuse me. For the last scenario, for the changing basis, for the example given to us, which is 2 by 3, because here actually we can calculate 3 odd ratio, right? We can, but actually we'll only need the 2 odd ratio. In other words, like there's one, odd ratio is redundant. So I was wondering, do you also talk about a general case, say for example n by m, and it's gonna telling us how many redundant the odd ratio we do not need to worry about.
Yeah. That's right. So the other thing to note is that when we use models like inherently ordinal models, or even partitioning models, or baseline, in any of these, one of our goals will be to reduce the number of parameters. That is, pretty quickly in such a model, we're going to get an explosion of number of parameters, and the fewer parameters we can put into our model, the stricter it is, the more it's actually saying about the data, and it's also a way to sort of compress our degrees of freedom, right? Just like we could get more power by looking at a linear model, or a model that's inherently ordinal versus one that's inherently categorical, because it reduces, say, all of these to being one, I have some constant change across all of these. And that sort of compresses the degrees of freedom and can give me more power. So we're going to try to do that as well. Okay, so let me start with the idea of partitioning. So the example is a medical study, say, where our response has to do with cancer. So maybe y equals 1 is that the patient is alive. Y equals 2 is that dead, not cancer. Y equals 3, dead, cancer, but not leukemia. And y equals 4, so sort of a study about leukemia, presumably, dead from leukemia. And then we have a predictor. There's going to be exposure to radiation, low, medium, high. And so the sort of analog of doing a partitioning model when we're thinking about the joint for a logistic regression is to break up our logistic regression into a series of stages. So we have the whole population, and we have sort of stage 1, we split the population into, are they alive or are they dead? So we group all of these 3 categories together. We collapse them. And we run a whole logistic regression, right? Just like we could do an analysis on the 2 by 2 table, we could convert our analysis, a 2 by 2 analysis, into a logistic regression. The odds ratio will be, log odds ratio will become our coefficient. So that's something sensible to do, and that reflects this collapse. And then we do another one on the collapsed variable, breaking it into, say, death from non-cancer causes and death from cancer causes. All right, so now we're looking at inside the collapse table. So this is a 3 LMH, and we have 1, 2, 3, 4, which we're trying to predict. So first we go 1 against everything else. Then inside of 2, 3, 4, we're doing 2 versus 3, 4. So this is 1 versus 2, 3, 4, 2 versus 3, 4. And then we're still left with a partition table that we want to break up. And so that we do another stage where we go other cancer. And we do leukemia. So this is 3 versus 4. So essentially what we're doing is we're taking a multinomial distribution and we're factoring it into conditional binomial distributions. And we fit separately. Fit each. And we're factoring our overall likelihood function into 3 independent likelihood functions. This is the dual thing from the partitioning kind of arguments that you went through in an earlier homework, or the logistic regression version of that. Of course, not all data admits a partition that's theoretically sensible. And so we have other models based on this baseline idea or on this idea that apply to more general cases. So this next one is called a baseline category logit. So we're in the same situation where y has more than 2 outcomes. And we have some predictors, categorical or continuous. And what we do is we model the log odds with logistic regression, model the log odds versus a chosen baseline. So there's an example, extended example in the online notes about alligator food choices. What do alligators like to eat? And unsurprisingly, most of the time, alligators like to eat, fortunately not people, but fish. And so in that case, because that's what happens most of the time, you make that the baseline. And then the other things that it might choose to eat in different environments, I don't know, amphibians or whatever, become the different ones. But this is an example where it doesn't make that much sense. I guess you could partition to fish and non-fish, but for whatever reasons, it doesn't make that much sense to use a partition model in that case. So you choose a baseline. So what does that mean our model is? So we have some sort of unordered outcomes, and we want to relate them to our predictors. So we set one of these outcomes, like fish, to be the baseline. And then our model is that we look at the ratios for everything versus the baseline. And we say that that is equal to, where j is not equal to j star. And so here I is the row or observation. But this should be, generally this is something like, all of the outcomes that correspond to a certain row. So n, there's an ni, which is not 1, number of observations. You should think about this as there's a natural grouping of cases, right? All of the people, we have whatever variables we're measuring, all of the observations for which those variables have the same value go into one of these rows. And so P is the number of parameters, say a number of predictors, plus 1, the number of parameters. And so this model has r minus 1 times p free parameters. That is, for each value of y, we get an intercept and we get and we get for a beta for each x. So it's quite a lot of parameters. If you have enough data, that's fine, but we'll see in a moment that that there's various choices for reducing these number of parameters. Basically, we set some of them equal, or we change coordinates and then set some of them equal. So if we just did that, we could interpret the coefficients as follows. Kth element of the vector bj, which is the horizontal vector, because j could be baseline or something else, so that's one of the possible outcomes, is increase in log odds of falling in category A, the outcome falling in category J versus the baseline category J star, resulting from, so it's the change in log odds, the increase in log odds from a 1 unit increase in xk, holding all the other variables constant. So if I remove a variable, if I remove variable x1 from consideration, I want to take that out of the model, that's like zeroing out the whole column of vectors, of coefficients. And of course, I can choose any of these to be the baseline, depending on what I'm interested in. If I'm doing something which is ordinal, usually I'll choose 1 or r. If I somehow think of it as ordinal, like in the smoking model or something. If I was trying to go the other direction to predict how many parents smoke. And then you can compute from that the probability that gets assigned Pij x transpose I beta j over 1 plus xi transpose beta j for non-baseline categories, and then the baseline category gets a different value, just 1 on top. So this, yeah.
Excuse me, I was wondering, so I kind of lost about the notation for the J star. So
J star is the baseline category. So if the baseline category, if Y has R outcomes, like it could be 1, 2, or 3, J is just 1, say if 1 is the baseline. Okay, so we said this was a GLM, and we've been talking about GLMs. So just like any other GLM, I can use similar ideas to test goodness of fit. As long as and we have the same sort of problem, right? So if we have too many cases, if we have too many configurations of our predictor variables, then our expected counts will be kind of small and things won't work. So we want to look to get G squared and Pearson statistics. We want to look at expected counts, which is the number in that row times the estimated probability. And if this is big enough, bigger than, most of them are bigger than 5, then we can test against the saturated. So what's a saturated model? I have some number of predictor variables, right? which describe sort of all of the possible states of the world for which I'm trying to predict it, right? This is all the rows of the model. If I give each row its own parameter, so each row gets its own parameter, that will always fit perfectly, right? And then it's saturated. If I have fewer than that, the parameters turn out to be fewer than that because of, I've assumed this functional form, then it makes sense to do this test. If it were equal, then it wouldn't make sense. So in this case, the saturated model has number of rows times number of outcomes minus 1, because it's a conditional probability, right, given any row. So remember, there's n rows. And there's outcomes, 2, 3, 4. And each row has to sum to 1, because it's a conditional probability. That's all we're saying. So the saturated model has this many degrees of freedom. And this model has the degrees of freedom equal to n minus p r minus 1. And so as long as these things aren't equal, we can do a test. And we can compute a g squared to be twice sum I equals 1 to n, sum j equals 1 to r, yij log mu log yij over mu ij. And we can do a Pearson with Rij equal to observed minus expected over the square root of expected. So these are the Pearson residuals. And just as in the other cases, if the model is true and no more than 20% of our cells have expected counts below 5, and none are below 1. None of the expected counts are below 1, then it's approximately, these statistics are both approximately chi-squared with degrees of freedom equal to, of course, the difference between the saturated model, which fits everything, and our reduced polytomous logistic regression model. And of course, even if this is not satisfied, just as we were doing for the Donner Party case, we can still look at the changes in g squared, even if not. So you can still think about nested models, provided there's some difference. We can also get over dispersion. So we have some covariance matrix. Like that, our usual covariance matrix for a multinomial model. And we could get an actual covariance matrix that has larger variances than that. Of course, it only makes sense to think about over dispersion if we have grouped data. That is, we're sort of looking at a contingency table. We're looking at something like this, and we're not looking at the individual observations. So the ni's are all greater than 1. And of course, we had this discussion last time about the theoretical reasons for overdispersion. I mean, overdispersion and model of fit, or model poor fit of the model are sort of indistinguishable. You should try to distinguish them by convincing yourself that you've included everything you can include, and that there's not a specific latent variable that you need to account for and that could be changing your results, right? That would change your estimates. Yeah. Go ahead.
Yes, I was wondering, so by intuition, it seems to us that if we increase the number, the NI, we can, definitely gonna decrease the variance. But based on the formula, like you just write down the blackboard, it seems to us that if we increase the NI, it's gonna increase the variance.
Yeah, right, of course. So the variance increases with.
Yes,
with that.
it seems to us
That's
kind of
good.
contradictory with what we.
Certainly not. Well, you're confusing the variance of this amount, which is the outcome, with a variance of an adjusted outcome, a normalized outcome. If you normalize the outcome, the variance will go down or will converge, right? But for example, if I'm talking about how many coins do I flip, right? If I flip 100 coins versus 1,000 coins, the 1,000 coin case will have higher variance. Just the number will be bigger. But the adjusted sort of, if you adjust it into a scale of 0, 1, it'll be smaller, you know, or it'll converge to a normal distribution. Okay, so to do the overdispersion calculation, then we're just introducing a scale parameter into this, a new sigma squared sort of scale slack dispersion parameter. And the estimate, the usual estimate, or the estimate that you'll get if you ask your software to do this for you, will be to compute the Pearson chi-squared test and divide it by its expected value, which is the number of degrees of freedom of the model. Right? This number is expected to be 1.
Yeah, excuse me. So I was wondering for the denominator part, like I was still a little bit confused about how we get the degree of freedom. So for example, where does the capital N minus P come from? I mean,
Yeah, I encourage you to try working it out.
sure. But
Yeah.
I know that
Yeah.
I know R minus 1 comes from because we sum up all the cells equal to 1. So that means we take 1 degree of freedom of our model. But
Yeah, just try working it out. Okay, it's just a simple algebra. I don't know. We do it right now. Okay, so and again, this is an overdispersion situation, and so it doesn't affect our estimates. The point of this is to beta becomes quasi-likelihood, which is something we didn't discuss, but it isn't affected, but it does affect our standard errors and our hypothesis tests. And the adjustments we have to do is multiply the covariance matrix by covariance of beta hat, which is given to you by the software for our purposes, by this adjustment parameter, divide the residuals, by this adjustment parameter, and divide chi-squared, g-squared, delta x-squared, delta g-squared by this same amount. And again, it's kind of not an excuse to exclude important variables, but a way to sort of a last-ditch, attempt to fix your model, even when it's not available. So just, I'm not going to go through it in detail because it's best that you read it. But there's this alligator example in your preferred software, in SAS or R, which you should check out in order to understand what's happening. But I just want to talk about it a little bit. So in this case, the food choice is the Y. And it's fish, invertebrate, reptile, bird, or other. I guess people go in other. And the predictor variables are XIR. Oh, let's not say XI. So the X's are, there's 4 lakes that this data looks at. There's size and gender. And you get a table of outcomes. And I just want to talk about how to interpret things. So we said that in this model, because there isn't a clear ordering, we're going to use this baseline model. And fish is the baseline. So P1 is probability that fish is the preferred food of this alligator. And then we have logit equations, Pj over P1. And we say that this is equal to some intercept plus beta 1 times x1, and so on. And so, okay, so here lake, there are 4 lakes, and there are 2 sizes and 2 sexes. And so for this, we can just use an x that's either 0, 1 or 0, 1. And for this, we have to do our usual trick of using a dummy variable. So we'll code one of the lakes as all of them being 0, and the other lakes as 3 dummy variables. So you can think about it as for, there's a lake 2 variable, there's a lake 3 variable, a lake 4 variable. If all of these are 0, that means we were in lake 1. It's the same sort of coding trick. Okay, so that means in total we get 6 coefficients: lake, size, gender, and an intercept for each of the logits. And so we have 4, this is 6 times 4 possible outcomes, 6 of these, so we get 24 parameters. And there are 16 cases or profiles, right? 2 times 2 times 4. And we should hope that for some of our tests to work, that the counts in each of these cases are reasonably high. So you can read about how to plug that into your software. And then we get degrees of freedom. So what's the so if I plug this in and my software spit out, okay, g squared was equal to 50. How many degrees of freedom should I think about that corresponding to?
Yeah, I was wondering what account is 16 minus 6 times 4 minus 1. Yeah, because 16 is the total number of cases.
Okay, so that's one proposal, right? Saying it should be n is 16 minus p, which is, what is p here? 6, right? times 4 minus 1. Is that what you're saying?
Why would it not be 5?
5 minus 1. 5 minus 1. So what's that? It's 40, right? 5 minus 1.
So that P is the parameter, right? Not the predictors.
P is the number of, well, it's the number of, it's this number. It's the number of x's after I encode the dummies.
That thing is intercept, right?
Yeah, the alpha is the intercept. Yeah. So this, it's the number of parameters that I get for each row, basically.
Yeah, sorry, excuse me. I was wondering, so how many, I was a little bit confused about the interaction. How are we going to code it? I mean, how many interactions are going to include?
So far we haven't included any interactions. Yeah. So that's right, it's 40, so it's 40 degrees of freedom in this case for the test. And then if you throw this into your software and you compute the coefficients, you'll get a whole bunch of coefficients. You know, estimate of a beta. For a beta, for example, size. Let's see, size, food, right? Size by food. And you'll get, let's see, with size being, so size is binary, and size, say food is equal to food number 2, I'll get minus 1.3 with a standard error of 0.4. And so that will be a significant coefficient. So I get a huge table of these, one for every coefficient. And some of them will not be significant, like the beta for gender and food equals 3. We get a 0.6 for the estimate and 0.68 for the standard deviation. And so that would be not significant. And so, you know, we do some model selection. We can decide, for example, if all the gender coefficients are 0, maybe throw out. And let's just look at what one of these resulting equations, once I plug all that into coefficients, I would get something like probability food given lake, sex, and lake size and gender over probability of baseline food, which is fish, baseline lake, size, gender, or not baseline, sorry, same lake size and gender, but fish versus arbitrary food. So these are the two things that are changing. And that would be equal to the alpha of the food that's changed plus a beta for a lake, food, plus beta for S, this food, S, and the beta, G, food, S, food, G. Yeah, so you get some coefficients. It doesn't make that much sense to talk about on the board, but I encourage you to look at the outputs. And of course, you'll have to do one of these in the next unit homework. And to analyze such a model, let's say analysis. We would just make a bigger version of one of these analysis of deviance tables. And we look at a nested set of models or a partial ordered set of models, a G squared and degrees of freedom for each of those. So we get a saturated model, which has 0 as this and 0 degrees of freedom left over. We have a big model like lake plus size plus lake times size. I'm going to leave that blank for a second. Lake plus size plus gender, which is the one we just did. And that would be 50.26 with 40 degrees of freedom. I could drop gender after seeing that the coefficients are not significant and get 52.48, 44. Lake alone, size alone, gender alone, 101.6, 114.7, and 116.7 at the bottom. Nothing. Degrees of freedom 48, 56, 56, 60. Okay. And from such a table, you can, as we've been doing, make calculations like now we have a delta G squared of about 2.2 with degrees of freedom 4. So we can see immediately that this is, formally says including gender, both lake and size, does not give a significant reduction in deviance. The other thing we need to note about this example is that your software will sometimes feed you garbage. So in SAS, it'll give a warning, and some of the R software will get a warning, some of the R softwares it won't give a warning, which is that when this coefficient of interaction is included, I think this is also plus x plus that, the model actually fails to converge or gives sort of nonsense answers. And in the example in the book, using one of the R packages at least, it doesn't warn you that the result is nonsense. You have to look at the output and decide for yourself that the result is nonsense. And what's happening is that effectively it's looking at some of the cells which have 0 entries. And that violates the assumptions of the engine that's doing the optimization. And so one way you could tell that is that for most of these coefficients, we have standard errors of around less than 1 and coefficient values that aren't too huge. And if you run that, you'll get one of these coefficients. It says that the estimate for the interaction term is minus 18, and the standard error is 1491.2. Okay? So when you look at that, you say, okay, when we did all these other examples, our standard errors were less than 1, and that's sort of a reasonable thing for a beta. All of a sudden it explodes like that and the standard error goes crazy. What it actually means is that it could be that the optimal point when you set up this model is actually like at the boundary or out at infinity. It would send this parameter to infinity, maybe send another parameter to negative infinity, like when you have collinearity in a regression. And you have two things that depend on each other. And the model, you have to use some additional constraint to get rid of the fact that they can just send those two parameters in opposite directions, right? Like if you have two predictors in a regression, which are equal to each other, you can cancel them out. Right? You can send one parameter to infinity, the other parameter to negative infinity at the same time, and those will all be valid models. So that's what's happening here. And this is a situation where you always have to look at the output that you get and ask yourself, is this a reasonable answer, or is this clearly nonsense?
Yeah, excuse me. I was wondering why the degree of freedom for the second model is 0. How we got to 0?
Well, it's not really zero. I mean, the test degrees of freedom is 0. The degree of freedom of the saturated model is not. It's 64 or something, right? Yeah. Or 60, depending on which one. 60, I guess. Right. So in one sense, you could think about it as so this number and this number are always fixed by the model, right? One of these numbers is always all the degrees of freedom available, right? And one of them is 0. And so whether you think about it as being 0 or 60 depends on just whether you're focused on the change in degrees of freedom versus the saturated model, or whether you're focused on the absolute degrees of freedom, like the dimension of the model. And you could throw in a dispersion parameter for this example. For example, if you see that, What do I want to do? Yeah, I'll let you read about that. You can adjust it for over dispersion. There's some reasonable reason to do that, but it's maybe not that interesting. So let's go to that was all about the baseline model. So let's go to the next one, which is this picture, where I have my response, and I want to compare adjacent categories. And one of the nice things about this is that there's a natural way to reduce the number of parameters. So we had a lot of parameters in that model, and we'll get the same number in this, right? Because it's totally equivalent to talk about baseline versus each thing or each jump. Right? Those, once you know either of those characterizations, you can compute the other one. But we can also reduce that. So here we're saying that we have a bunch of logits like P1 versus P2, P2 versus P3, and finally PR minus 1 versus PR. And then we say that each of those things is equal to some coefficients, beta 1, 0 plus beta 1, 1x, and so on. Beta 2, 0 plus beta 2, 1x, 1 plus so on. Beta r minus 1, 0 plus beta r minus 1, 1, x1, and so on. Right? That's our model. And if you look at it for a while, you convince yourself that these, just as we knew in the contingency table case that once I know all the odds ratios from one point of view, I can get them from the other point of view. These things are just linear transformations of the ones from the baseline category model. Namely, kind of log P1 over P2 is minus L1 over here. Log, of course, that's the same thing. Log P3, P2 over P1. P3 over P1, so that's a different. Right? That one I get by just combining those two. I just add them up or multiply the odds ratios. P4 over P1, etc. Right? Minus L3, minus L2, minus L1. Okay, but the new thing that we can do to reduce the number of parameters is we can take this big matrix of coefficients here and say, you know what, let's for each of the categories, the jump in each categories, let's let the coefficients, the intercept vary freely. But then let's say the effect of x1 should be the same. In other words, when I jump up by one category, no matter which category I'm at, right, whether I'm making this jump or this jump, I'd like the effect of an increase in x1 to be the same. So I'm going to set all of these equal. And that leads to a simplified model, which looks like this first ratio is equal to some intercept plus beta 1 x1 plus beta 2 x2, and so on. L2, a new intercept for L2, but then it's still beta 1 x1 plus beta 2 x2, and so on. So we've let these coefficients be equal and vastly reduce the number of parameters. So what we're saying is that if we hold all the x's except x1 constant and increase x1, then each adjacent odds ratio is equal to just e to the beta 1.
Yes, excuse me.
Yeah.
So I was wondering, we got the log P2 over P1 equal to minus L1. So I was wondering the coefficient L1, sorry, the minus one basically is comes from the reciprocal of.
Yeah, that's right, because this is 2 divided by 1, this is 1 divided by 2. So
Yeah,
we're just
so
changing
we
this.
take the reciprocal and then we take the log that is come from the, that's the
Right.
reason why we have minus 1.
That's right. So what we're saying in the table, again, is that, so in a generic model where we're looking at these odds ratios, right, we have these cross products, and we're comparing, where we get a theta for each of these. 1, 2, 2, 3, 3, 4. And this model is just saying that these are equal. That's what it means to make this beta equal. For adjacent odds ratios are equal. These are equal, but if I multiply them all together, like I compared this to this, it would depend on how many columns I've crossed. Right? So this is inherently ordinal. So we're saying that the log odds of falling into category j plus 1 versus category j when x1 increases by 1 unit is some number, beta 1, and is fixed. So let's introduce another ordinal trick we can do, which is actually different. So those two are sort of, well, they're equivalent, and then you restrict it to make them not equivalent. Here's another model which is about ordinal data, but which is not equivalent. And the idea here is that the comparisons to make, so I have some y with r outcomes, and they're ordinal. So I can compare outcomes. Then I can take the log probability that y is at most j divided by the probability that y is greater than j. Other ways of saying that is that this is equal to log y less than or equal to j divided by 1 minus y less than or equal to j. That's why it's a logit. Or it's the log of p1 up to pj over pj plus 1 up to p, however many categories there are. This is the r. Right? And so the idea here is that instead of modeling adjacent things, we're going to say we have a big table. Right, this is the predictions, this is my outcomes, and I'm going to think about all the possible ways to split this table into two halves. This half and this half, this half and this half. That's going to give me a bunch of odds ratios. It's kind of like the combination of a partition and an adjacent thing. That'll give me a bunch of odds ratios, and then from those I can construct logits, and from those that I can predict for the systematic component. Once I do that, I can also add further restrictions. Like I might say that all these partitions have to have the same value. So this So we take each of these, we take each of these guys and we put them equal to some, so P1 versus the rest, P1 and P2 versus the rest, log P1, P2 up to PR minus 1 versus PR, and then we set each of these equal to something linear. Beta 1, 0 plus beta 1, 1, x1 plus beta 1, 2, and so on. Right. Set each of these guys equal to r minus 1, 0 plus beta r minus 1, 1, x1, and so on. So we model each of these sort of partitions, bipartitions of the table as its own logit. And this one is fundamentally different, doesn't have a linear transformation into the other guy. And we can again make this restriction to set all the beta equal in a column. That is, say that our model for L1 is actually some intercept plus beta 1 x1 plus beta 2 x2. And this no longer, these betas no longer depend on the row. And this has a name, it's called a proportional odds or cumulative logit model. So let's try to think about what it means. Okay, so alpha j log odds of being in or below category j for my outcome y when x, all the xi's are 0. And then a beta. Okay, so this is increase in the log odds of falling, of this, falling into or below. With a 1 unit increase in xk, holding the rest constant. The rest of the x is constant. Okay. So that's kind of a mouthful, but that's the model. Let me just say one other way of saying that. So the odds ratio is proportional to the difference between the outcomes category like x between x1 and x2. So at the, this is with a continuous variable or with a non-continuous variable. So beta exp beta x1 minus x2. Okay. I'm going to stop there. We'll leave some time for questions and stuff. I'll continue next week with more of lesson 8, and maybe a little bit of review if you think you need it. Although I guess we'll be into the midterm, so that might be not really that useful. And we'll get ahead. So now we'll be by the end of next week, we'll be ahead by 1 lesson or so of where you are in the homework, which hopefully should make things a little bit easier.